Okay, in this lab, we are going to react magnesium with HCl, and we're going to do it so that the gas that is produced is collected within this gas collection tube. The gas collection tube needs to be completely filled with liquid so that any gas that's produced displaces the liquid and is the only gas inside the tube, right? So I can't leave air in there. We also have to make sure that we know how much of the magnesium we actually have, and we have to keep it separate from the HCl before the reaction takes place. So there's a lot of things that we have to take care of, and one of the first things we have to do is measure our magnesium. So what we do is we just measure it with a ruler, and we find that this one is 24 millimeters long, right? So if we hold it up here to a ruler, you can see that it goes to 24 millimeters. Let's see if we can hold that better. There we go, something like that. You can see it's 24 millimeters. And so 24 millimeters of magnesium. And we will write that down on the old lab sheet. So 24 millimeters of magnesium. And the reason we care about that, right, the reason we care about this is that it turns out that we measured 1,000 millimeters or 1 meter of magnesium ribbon, and it turns out that it weighs 0.889 grams. With those two pieces of information, we should be able to figure out what the weight of our little strip of magnesium is, and that's going to be part of the lab report. So after we measured that magnesium, we are now going to tie a knot around it so that it can't get loose. And that's a little awkward, but it can be done if we simply use this thread that we are given here, wrap it around a couple times, and tie a couple half knots to hold it in place. And so now we have our magnesium ribbon, which is in place here, and then we're going to tie the other end around the end of this tube. So we'll flip this tube over, and we'll tie the other end around here. And again, just sort of wrap this around a little bit and tie a couple half knots. And now we have our magnesium ribbon, and it's all secured, and we can use it later. It will react with the HCl later, right? So first we need to pour HCl in here. And we have a pre-measured amount of HCl. It's about 10 milliliters of 3 molar HCl. Right? And so we'll pour our hydrochloric acid into the bottom, and you can see that we have just about 10 milliliters of HCl in there, right? Just about. And we will then pour water on top, right? But we'll pour sort of gently, and what will happen is the HCl will stay at one end of the tube, and the water will fill the rest, so that when we put the magnesium into the tube, it will only be touching water, not touching the HCl, and so the reaction won't start until we flip the tube over. That's the benefit of this. So we fill it with water, and I'm going to put my beaker down. And at this point, what I'll do is I'll tuck the magnesium ribbon in to the gas collection tube, shove a little, right? Put our stopper in, put our finger over it, and turn it over into the liquid, right? At that point, the hydrochloric acid starts falling, and it will get down to where the magnesium ribbon is. Now let's see if we can zoom in a little bit on that and see what it looks like as it's falling. And there's the ribbon. So let's bring this up a little closer. And if we look along the tube, you can see ripples in the water where the hydrochloric acid is falling, because the hydrochloric acid is more dense than the water, And so it looks like little ripples as it falls, even though it's a colorless liquid. As it falls, you can see it as these ripples falling through the water. When those ripples get far enough down, you can see that there are some down there. When they actually get down to where the magnesium is, then the reaction can start. At this point, you can see that the magnesium is starting to bubble because it's reacting with the hydrochloric acid, the HCl, and the reaction is starting. The gas is trapped in the tube because the reaction is is wholly inside the tube, and so the gas rises to the top. You can see that there is that stream of bubbles going up to the top. And the gas is starting to collect up there. It does not break the tube because the bottom of the tube is open, so the liquid simply leaves the tube, right, as the gas displaces it. Okay. And when the reaction is over, we can tell what volume we had, so we can measure volume. Okay. So we just need to wait for that to finish. Now, the gas and the water are at about the same temperature because the gas is bubbling through the water. And so we can tell the temperature of the gas by saying that it's the same as the temperature of the solution that created it. Further, we can wait a little bit after the reaction is over to let it equilibrate, and so it can stay at about room temperature. But we'll measure what that is with the thermometer here, and we'll let it stir a little bit to make sure that we have the temperature. And at this point, we can see that the temperature is right around 21 degrees or so. So we hold it up here. If we wish to be clear on this, let's see if we can do that. Whoa. Come on, you focus. Whoa. Maybe, maybe not. Maybe it's better to just read it. But it's just about 21 degrees. Okay. So we'll write that down, 21 degrees. And we'll set our thermometer to the side. We also need the atmospheric pressure because we need to know what pressure is pushing in on our gas. And so we will use ye old interweb, and we will go to, I don't know, some weather site and get the atmospheric pressure from there. If we set the units to degrees Celsius for the temperature on the weather site, it'll give us the pressure in metric units. And we can find that today's pressure is, if we look at this, whoa, whoops, 1020.3 hectopascals, which is the same thing as 102.03 kilopascals. And so we'll write that down. See this, the reaction is still going. And we've already got something over 10 or 11 milliliters of gas. You can see the water level going down, right, as the gas is being produced. Okay. So at this point, all we need is the final volume of the gas, and we just need the reaction to finish. Some of the magnesium is floated up towards the top, and that means that it was sufficiently thin that it broke off the string. So the reaction is just about done. And a little bit of magnesium that fell out of the knot in the string. Tap a little bit, see if we can dislodge some of those bubbles. But at this point, the volume is changing much more slowly. Tap a little bit, try to dislodge some of the larger bubbles. All right, but the reaction is basically over. So at this point, the total volume is just under 21 milliliters. And what we'll do is we'll turn this around and so we can zoom in on it, maybe. This might work better. So you can read the volume off of the graduated cylinder, off of the gas collection tube. And actually at this point, the meniscus is just slightly below the 21 mark, so it would be like 21.1. Yeah. It's like 21.1. So we'll write that down as our volume. 21.1 milliliters. So at this point, our data table, let's see if we can't zoom out, looks something like this. Okay, so we have 24 millimeters of magnesium ribbon. It was 0.889 grams for every 1,000 milliliters of magnesium ribbon. We collected a total of 21.1 milliliters of gas. The temperature of the solution and the temperature of the gas were approximately 21 degrees Celsius. And the atmospheric pressure today is 102.3 kPa. Okay, there are a couple things on this write-up that we want to pay attention to. One is that this is a single displacement reaction, and that will help you write the balanced equation for this. We know that it's producing hydrogen gas, and we know that a single displacement reaction is the reaction of an element, right? In this case, Mg, plus a compound, which in this case is HCl. And in an element and a compound, the metal, in this case magnesium, will displace the positive part of the compound, in this case H. Okay? Don't forget that it produces Mg2 plus ion and Cl minus ion, okay, so that we'll get those as products as well. When you're done, do not forget to balance. Don't forget to balance the reaction, okay? You will need to figure out the mass of magnesium ribbon. in this case, I would set up a factor label problem starting with 24 millimeters of magnesium ribbon. And you would set up a factor label problem because you are looking for grams of magnesium ribbon. Okay. Again, when you're doing stoichiometry, you're going to set up a factor label problem to solve for the moles of H2. But in this case, you're going to have grams of Mg, so I would start with grams of Mg and then set up a factor label problem to get to moles of H2 gas. Okay, so that will be how you solve this problem. If you were to turn this over, you'll see that the top part is all focusing on pressure. Now, it's a little bit awkward because we haven't talked a lot about collecting gases, but in this container, you've got a gas collection tube, right? But inside the gas collection tube is a bunch of water, right, which is a liquid. But you also have water vapor. And you also have your hydrogen gas. The total pressure inside the container is the same as the pressure outside the container. Outside the pressure, you have the pressure of the atmosphere. And so you know that the total pressure is equal to the pressure of the hydrogen plus the pressure of the water vapor. We don't have an easy way of measuring the water vapor. We do, however, know that the water vapor is determined by the temperature of the liquid water underneath it. And so we can simply use this chart to find the water vapor pressure. In this case, it's given to you in millimeters of mercury. So if we know our temperature, we can find the pressure of the water vapor over the liquid water that's mixed in with the hydrogen gas. So for the water vapor, we would find whatever our water vapor is in millimeters of mercury, and here you would have some number of millimeters of mercury, and you would set up a factor label problem to convert it to, and we're looking for atmospheres. Okay, where would I get this number? Well, this number I would get from the chart. Okay, so I would have to look up my temperature to find what the vapor pressure is. For the atmospheric pressure, we took that off the internet, and that would be some number of kPa. And again, we would set up a factor label problem and convert it to ATM. In this case, our kPa, I believe, is 102.3, and it was. So we would then have 102.3 kPa. And so we would convert that to atmospheres. At the end, we can use this relationship that the pressure of the hydrogen gas is equal to the difference of the total atmospheric pressure minus the vapor pressure. And that would give us the pressure of the hydrogen gas. So the atmospheric pressure minus the vapor pressure. Okay. Now, we're going to try to solve for an experimental value for R, the ideal gas constant, and so we'll use the values that we've collected. We know that PV equals nRT, and so what I would like you to do is rearrange the equation for R, right? So R is equal to, and set up an expression for R. Then you can plug in the numbers from the lab. But it's important that you recognize that you want V, P, N, and T all for hydrogen gas. Okay. We have three pressures. You need to make sure you select the proper one. Lastly, we're going to look up the formula for percent error, and you can then compare your value that you get for R to the true value, or to the accepted value, which is 0.0821 liter atmospheres per mole Kelvin, or 8.31 kilopascal liters per mole Kelvin. At that point, we are done. So hopefully that was helpful.